Yo, what is up? In this example, we're going to be looking at the connection between position, velocity, and acceleration. So to begin that, we need to talk about the relationship, and this function is called h of t, so I guess we could start there. The relationship between a position function, like this one, and a velocity function and an acceleration function. So the connection here is that the velocity would be the derivative with respect to time of that position function. And then the acceleration would be the derivative of that. So the derivative of the derivative there, no big deal. So today we're going to be connecting those things. And what else? What else can we say here? We can say that the h of t in this situation tells us the height or the position of whatever the object is, while the velocity tells us how it's moving. Tells us how the object is moving, what direction it's moving based on the sign, how fast it's moving. So the velocity tells us how the thing is moving, and acceleration can tell us a little bit more. When we connect the acceleration and velocity, we can determine if something is speeding up or slowing down, depending on those signs. So let's check out this first example. First one says, find the instantaneous velocity at any time t. So if I want to find the instantaneous velocity and I'm given a position function, I know I have to do the derivative of that position function. All right, so whenever we find the derivative of that, we can call that our velocity. So we could make this look a little bit prettier. We could say that the derivative of h prime, is equal to our velocity. Cool, so when we do the derivative of that, we're just using the power rule. So 1/3 t cubed, using the power rule. So we'll multiply by 3, and 3 times 1/3 is just a 1 t squared. Knock the degree down one notch. So and then up next, our next term is negative 3t squared. So the derivative of that, following the power rule, is negative 6t. And then the derivative of the next term, 8t, would just be 8. So our velocity function looks pretty darn good. So at any time t, we know the velocity would follow that formula, that function. All right. Moving on to the next one. When is the submarine momentarily at rest? So at rest means it's not moving, right? So remember, if we're talking about moving, we're talking about the velocity. So I need to know when the velocity is equal to 0. So it's always good to underline and text mark and say, okay, I want to know when v of t is equal to 0. So we already knew v of t from the last example. I think we said that it was t squared minus 6t plus 8. And now we know we need to find when that velocity is 0, because our particle is at rest. The velocity is 0, the thing's not moving. This looks like it might be factorable. So maybe we got a t minus 4 and a t minus 2. That looks good. So, according to our zero product property, we know that the velocity is equal to 0 when t equals a positive 4 and when t equals a positive 2. Cool. And those are both in our domain because we want to know time has to be positive, right? We're not going back in time. So this particle is at rest after 2 seconds and after 4 seconds. So there's 2 times when our submarine is at rest. I guess I should write it. Submarine is at rest at t equals 2 and t equals 4 seconds. Because v of t, which is equal to h prime of t, is equal to 0. Cool. So that's a super well thought out, explained answer. Very cool. Now you can think about what this submarine might be doing. Why is it at rest at those times? Maybe it's changing directions. So if we were to determine that, we'd probably make a sign chart and see if V of t was changing signs around 4 seconds and around 2 seconds. Our next example, find the acceleration. Okay, so we know that h prime is equal to v of t, and that was t squared minus 6t plus 8. So on this one, we got to take it a step further because we're talking about acceleration. So we're doing the derivative again. So we would say the second derivative of h of t is equal to a of t. And it's going to be the derivative of this. So again, using the power rule, 2t minus 6. Oh, that was it. That was fun. So at any given time, the acceleration is modeled by 2t minus 6. Cool. Next example. What is the displacement? Okay. The displacement, not really much of a calculus question here. Displacement is just our change in position. So let's write that. It's our change in position. So not really a calculus question because we're given the position formula. So I just want to know over the first 4 seconds. So how far did I move? What was my position at 4 seconds? And we'll find the difference of that in our position at 0 seconds. So I will have to plug that in. That's going to take just a second. Let's see, at 4 seconds, I got 4 cubed. What is that? 64, 1/3 of 64. I'm not real sure what that is, so I'm just going to write 64 thirds. And then I've got minus 3t squared. So that'd be 4 squared, 16. 16 times 3 is 48. And then plus 8 times 4, 32 plus 5. So if I just kind of combine like terms over here, I could say that h of 4 is 64 thirds. And then I could just simplify all this up here. Negative 48 plus 32 is negative 16 plus 5 is negative 11. So h of 4 is this. I don't have a calculator in front of me, so that's the best I can do. Minus h of 0, much easier to find. Throw a 0 in there. H of 0 is 5. So my displacement is that. And I guess I could simplify it a little bit more and say 64 thirds minus 16. I could make a common denominator. Oh man, I could have left it too. That's the great thing about calculus. 48 thirds and 64 minus 48 is 16 thirds. So if I'm going to answer this problem, I could do it in a nice way. I could say the displacement of the submarine is 16 thirds, and they were measured in meters, so it moved 16 thirds meters over the first 4 seconds. Very cool. All right, well, that's everything. Hope you learned something. See ya.